Hi all. We finish up chapter 9 on different differential equations. 9i is about uh, two, a plane representation about how your gradient looks like. So it's called a slope field. You have your differential equation, you have your first derivative that is a function of um, it could be x and or n or y. Okay, in this situation, when you have a differential equation equals to just a function of x, what it means is for a specific value of x, the derivative, the gradient is the same. So let's say I set x equals 0, dy over dx is equal to 0. Now for x equals 0, it will be on the y-axis, and what you would do is, as your differential equation is equal 0, which is horizontal, you have those little horizontal dash, and for the same x, independently of the y coordinate, it will be exactly the same. Okay, if I set then x equals, let's say, 1, the derivative is equal to 2. So let's say we're over here, and what you do is you will have you just approximate to make it a gradient 2 to 1 using your Cartesian plane. So here for, let's say, x equals 1, the y is equal to the gradient of the tangent is equal to 2. So we have the same sort of dash with the same orientation, the same angle. As x increases, so you move to the right, you can see the gradient, those little dash are getting steeper to a point when it's infinity. On the negative side, it's negative, so it's going downwards. Okay, and as it is a function of x, independently of the y, you'll get the same. So as I draw imagine a vertical line anywhere, the gradient of the tangent is still the same. Okay, so that gives you an infinite number of curves. Now you can see a little bit of a pattern that looks a little bit curvy like that, which is a parabola, because if you remember, if you anti-differentiate that, that gives you x squared plus a constant. The fact that it has a constant shows you that field. It shows you an infinity number of parabolas. Okay, it's infinite. The only way you can narrow it down to one simple parabola is having a initial condition. If you were to use integral, you will have boundaries or a definite integral. But let's say we define a point 0, 2. What you do is you go on your Cartesian plane 0, 2, that gives you a point here. From here you can extrapolate the rest of the parabola. It's kind of a bit like the Euler's method. You have a starting point, you use the gradient, you determine the next point, and so on. Okay, and you get your unique parabola. Most of the technique you would use is a CAS calculator if the rule is given to you. But if you have a graph of a slope field, then you will have to scan it and move along the curve. Okay, first example of 2, you have a differential equation which is dy over dt equals y. So notice now this function is dependent on the y. What it means is it will be independent of x. So as you move along across horizontally on your graph, you should have the same gradient. And on the plot of the slope field, plot the graphs of the particular solution. So 0, 2 and 1, negative 3. Let me hold on. So here, what you would do on the cascade, you need a graph page. You select menu, graph, entry, edit. You pick differential equation, and you enter your differential equation. What's given to you is y1 with a dash. So on the right hand side, make sure you write y1 or select y1. I think if you press tab, you get the list of possible variables. You press enter, it shows you the slope field. So as I said, because it's a function of y, as I move across for any x values, you can see the gradient of the tangent will still be the same for the same y value but different x values. Alright, we do part B. To do part B here, you go back to the graph entry line by pressing tab. As you arrow up to y1 dash, you can enter your initial conditions. So the first one, you 0 tab 2, then you can add more points by clicking the green plus icon, 1, negative 3. As you press OK, it shows you the two curves with the initial conditions. So that's your 0, 3, and that's going to be your 1, negative 3. You can also grab those points and drag it to change it to a different initial condition. Alright, last example. So here you have a different differential equation, kind of a little bit more complicated because it will depend on x and y, so it's kind of harder to visualize. So I recommend to use the CAS calculator to do that. Again, you go through the same sequence of menus. You type in your differential equation. Notice for the y variable it's a y1. For x, it's just the standard x variable. You enter your initial condition and you press enter. So here you will have your curve, okay, in red. Notice also you will need to set your windows, otherwise if you don't set your windows you could be too far on the left up here on the right, so you need to set your windows within this interval, or zoom in or zoom out to make sure you get the curve in your view. Alright, next one is a kind of an exam question where in that situation you can't use your CAS calculator. You have a slope field, but the equation is not given to you, so you can't enter in on your CAS calculator. It tells you that the solution, which is when you have a slope field, it's an infinite number of solution, but this solution is narrowed down to 1 because it needs to go through that point. Now, as it goes through that point, it's asking you, does it go through which point on the as a choice? So here what you do is you have your those are your answers. You place your point, and what you need to do is scan through. Similarly to your Euler's method, you move along the curve. So let's say you have 0, 2 is a potential solution. As I move here, I'm going to try to get to x equals 0. So I scan through here, I move along, and I get here approximately here. It goes up a bit, maybe here. So you can see when x equals 0, the y value will be 1. So that would straight away exclude 0, 2. So as you keep moving, you can look up the different solution. The one that is definitely the one I was working out will be that 3, negative 0.5. As you go downwards, it will exclude that one, it's too far up. And D will be your choice as a correct answer, which would be D for this question. And that's all I have for today and chapter 9. See you later.